In this video, we're going to go over fluids. We're going to talk about density, buoyant force, Archimedes' principle, Pascal's law, hydraulic lifts, Bernoulli's equation, and things like that. So the first thing that we need to talk about is density. The density of an object is the mass divided by the volume. This symbol is also known as rho. Now don't confuse it with pressure, which I'm going to use capital P. Now if you rearrange the equation, mass is density times volume. The density of water is about 1 gram per cubic centimeter. This is also equal to 1,000 kilograms per cubic meter. The specific gravity of a substance is the density of that substance, let's say substance A, divided by the density of water. So for example, if the density of aluminum is 2.7 grams per cubic centimeter, what is the specific gravity of aluminum? It's the density of aluminum divided by the density of water, and it's simply 2.7. So the specific gravity compares the density of a substance with that of water. Let's try this problem. What is the weight of air inside a spherical balloon of radius 2 meters? And you're given the density of air. Ignore the mass of the balloon. Feel free to pause the video and try this example. So let's say if we have a balloon that has a spherical shape, and there's gas particles inside the balloon. And the gas, even though it's light, it does have mass, so it exerts a downward weight force. What is the weight force of those gas particles? Well, we know that weight is equal to mass times gravity, and mass is density times volume. So the weight of the air inside the balloon is the density times the volume times gravitational acceleration. So it's 1.29 kilograms per cubic meter. That's the density, but we need to find the volume. The volume of a sphere is 4/3 pi r cubed. The radius is 2 meters. So 2 to the third power, that's 8. 8 times 4 is 32. 32 divided by 3 is 10.67 times pi. This is about 33.51 cubic meters. So that's the volume times the gravitational acceleration of 9.8 meters per second squared. So if we multiply these three numbers, this will give us a weight force of 423.6 newtons. Now let's talk more about density. So let's say if you have a beaker containing water, and the density of water is about 1,000 kilograms per cubic meter. Now let's say if you place a chunk of aluminum, what's going to happen? Will it sink or float? The density of aluminum is about 2.7 grams per cubic centimeter, which is 2,700 kilograms per cubic meter. So because aluminum has a higher density than water, it will sink. But let's say if you place an ice cube in water, ice floats on top of water. The reason why ice floats is because the density of ice is less than water. The density of ice is about 917 kilograms per cubic meter. So about 91.7% of the volume of ice will be below the surface of water. So as you can see, heavy objects sink and light objects, they tend to float. Now the same behavior is true for gases. Let's say if you have a balloon that contains helium. Helium is lighter than air, and so helium is going to rise. Now if you have a balloon containing carbon dioxide, it's going to sink. Carbon dioxide is heavier than air. Air molecules are mostly composed of nitrogen and oxygen gas. If you look at the periodic table, oxygen has an atomic mass of 16 times the 2 oxygen atoms that you see here, so the molar mass is about 32 grams per mole. For N2, it's 14 times 2, it's 28. Now, air is about 78 to 79% of nitrogen and approximately 21% oxygen. There's some other gases too, but it's around this number. So we'll say that nitrogen is 78% and then the other 1% is the other gases. So the average molar mass of air is somewhere between 28 and 32. The molar mass of helium is 4. The molar mass of CO2 is 12 plus 16 times 2, that's 44. So because carbon dioxide is heavier than air, it's going to sink. But because helium is lighter than air, it's going to rise. Another fun fact about air is temperature. Hot air rises and cold air sinks. In hot air, the gas particles are further apart, and so hot air is less dense than cold air. In cold air, the gas particles are closer together, and so cold air has a higher density than hot air. So hot air tends to rise, cold air tends to sink. If you live in a 3-story apartment or house, if you turn on the AC, you'll realize that the first floor, or even the basement, will be the coldest area in the house, and the attic is usually the hottest part of the house. That's because all the hot air rises towards the attic and the cold air sinks towards the basement. So this principle is useful for hot air balloons. For example, let's say if you have a very massive hot air balloon, let's say there's a torch. So as you heat up the air inside the balloon expands, and the hot air is less dense or lighter than the surrounding cooler air. So let's say the temperature inside this balloon is maybe 50 degrees Celsius, and outside, let's say it's 20. So as you heat up the air on the inside, the hot air will rise. Now, if you want the hot air balloon to descend, you basically turn this off, and the temperature will decrease, and eventually the weight of the balloon and this package or the people inside it will eventually cause the hot air balloon to descend. So by adjusting the temperature, you can control if it's going to ascend or descend. Now here's a question for you. Is it easier to float in pure water or in salt water? What would you say? So is it easier to float, let's say, in a pool versus the ocean? In a pool, it's mostly pure water. There might be some chlorine inside of it too. But for the most part, the density of the water that you'll find in a typical pool is about 1,000 kilograms per cubic meter. Now, the density of seawater, which is basically salt water, is a little bit higher. It's about 1,025 kilograms per cubic meter. So therefore, it's easier to float in the ocean than in a pool because the density of seawater is higher than that of a typical pool. Now, let's say if you were to go to a very salty lake water, let's say like the Dead Sea or something, the density of the Dead Sea is very, very high. Because it's so salty, if you were to jump in and try to swim to the bottom, you won't be able to. The buoyant force there is so strong that it's going to lift you back to the top and you're going to float right on top of it. The density of the Dead Sea water is about 1240 kilograms per cubic meter. And the higher the density of a fluid, the harder it is to sink. It's easier to float. So it's easier to float in seawater than it is to float in a pool. And by the way, a fluid is anything that could flow. So liquids and gases, because they can both flow, are considered to be fluids. Let's try a problem. An empty bottle has a mass of 25 grams. If you fill it with water, the combined mass is 95 grams. When filled with another fluid, the combined mass is 75 grams. What is the density of this unknown fluid? So what would you do in this problem? So we need to find the volume of the empty bottle of water, because if we have that, then using the mass of the fluid, we can calculate the density of the fluid. Now we know the density of water. It's about 1 gram per cubic centimeter. So what is the mass of the water? The combined mass of the bottle and the water is 95 grams, and the mass of the bottle is 25. So the mass of water must be the difference between these two values. It's 95 minus 25, which is 70 grams. So now let's calculate the volume. Density is equal to mass over volume, and volume is mass over density. So 70 grams of water divided by a density of 1 gram per cubic centimeter tells us that the volume of the bottle is 70 cubic centimeters. Now that we have the volume of the bottle, let's calculate the density of the fluid. So first, we got to find the mass of the fluid. The combined mass of the fluid and the bottle is 75 grams, and the mass of the bottle is 25. So the mass of the fluid is 75 minus 25, so it's 50 grams. Therefore, the density of the fluid is the mass divided by the volume. So it's 50 divided by 70. 50 divided by 70 is about 5 over 7, or 0.714 grams per cubic centimeter. Now that we have the density, if you need to change the units from grams per cubic centimeter to kilograms per cubic meter, multiply by 1,000. So this is equal to 714 kilograms per cubic meter. So that's the answer for this problem. 50 liters of water is mixed with 100 liters of alcohol. What is the density of this mixture? To calculate the density of the mixture, all we need to do is take the total mass, that is the mass of the water, plus the mass of the alcohol, and divide it by the total volume. Because density is the total mass of the solution divided by the volume, or the total volume of the solution. Now, the mass of water is the density of water times the volume of water. And the mass of the alcohol is the density of the alcohol divided by the volume of the alcohol. And we're going to divide it by the total volume. So let's separate this fraction into two smaller fractions. So it's going to be, to keep it simple, P1 V1 divided by V total plus P2 V2 divided by the total volume. Now the reason why I did it that way is so that you could see that it really doesn't matter what the units of volume are, because it's going to cancel. If it's in cubic meters or liters, it doesn't matter. It's the ratio that's important. So I don't have to convert liters into cubic meters to get the right answer. So therefore, the density of the mixture is going to be the density of water, which is 1,000, times the volume, which is 50 liters, divided by the total volume, which is 150 liters, plus the density of the alcohol, which is 790, times the volume of the alcohol, which is 100 liters, divided by the total volume of 150 liters. So we can cancel these two zeros. So the first part, 1,000 times 5 divided by 15 is about 333. So that's the contribution from the water. And for the other part, 790 times 10 over 15, it's about 526.6. If we add the two, it's 859.6. So that is the density in kilograms per cubic meter for the mixture. And it makes sense though. Notice that the density of the mixture is between the density of water and the density of aluminum. Now it's not exactly in the middle. If you average 1,000 and 790, if you add the two numbers and then divide by 2, the average between those two numbers is 895. Now, if we were to mix 50 liters of water with 50 liters of alcohol, then the density of the mixture should be 895. But notice that the density of the mixture is closer to the density of the alcohol. It's between 790 and 895 as opposed to 895 and 1,000. Why is the density of the mixture closer to that of alcohol? The reason for that is simple. We mix more of the alcohol than the water, so the density of the mixture should be closer to the density of the pure alcohol than pure water. Now let's talk about pressure. So pressure is the ratio between force and area. The unit for force is newtons, and the unit for area is square meters. The unit for pressure is pascals. 1 Pascal is 1 Newton per square meter. And 1 ATM, or 1 atmospheric pressure, is 101.3 kilopascals, kPa, or 101,300 pascals. Now you might see units of torr or millimeters of mercury. 1 ATM is equal to 760 millimeters of mercury, and this is also equal to 760 units of torr. Now these units are usually more associated with chemistry, but in physics, the standard unit for pressure is pascals. Now let's go over the concept of pressure. So let's say if we have a square that is 1 meter by 1 meter, and if we have a larger square that is 10 meters by 10 meters. Now if we apply a force of 100 newtons across the area of this square, and the same force of 100 newtons throughout this entire square, which one has a larger pressure value? Is it the one on the left or the one on the right? So pressure is force over area. The area for the square on the left is 1 times 1. It's 1 square meter. But for the figure on the right, it's 10 meters times 10 meters. So it's 100 square meters. So we have a force of 100 newtons being applied over an area of 1 square meter. So the pressure is force over area. It's 100 pascals. Now, for the figure on the right, 100 newtons is being applied over an area of 100 square meters. So 100 over 100 is 1 Pascal. So the pressure is significantly higher on the figure on the right. So if you apply a force over a very small area, the pressure is going to be very, very high. To illustrate this concept, let's say if you push someone with your hand and you apply a gentle force, it's not going to cause much damage. But let's say if you apply the same force but with a pen and you poke someone with the pen, which one is going to cause more damage? Pushing someone with your hand or applying the same force with a pen? Because the area of a pen is so small, and if you apply the same force over such a small area, the pressure is significantly higher. For example, if you push someone, let's say you apply a force of 100 newtons, and let's say the area of this surface is 1 square meter, the pressure is only 100 pascals. But now let's say if you apply a force of 100, and let's say this area is significantly small, let's say it's 0.01 square meters. 100 divided by 0.01 is 10,000. So the pressure is significantly larger because the area is so much smaller. And that's why poking someone with a pen causes much more damage than pushing someone gently with the palm of your hand. It's because you're applying a significant force over a very, very small area. So the pressure is very large. Now let's say if we have a rectangular box. And let's say the dimensions of the box are 5 meters by 4 meters, and it has a height of 3 meters. And let's say the mass of the box is 100 kilograms. Now, what is the pressure exerted by the box at the ground below? So let's say the box is on this horizontal surface. What is the pressure exerted in this shaded region? So we know that pressure is force divided by area. And the force exerted on the table in the purple shaded region is basically the weight of the box, which is mg. So the mass of the box is 100, the gravitational acceleration is 9.8, and the area of the bottom surface is basically the length times the width. We don't need the height, so it's 5 times 4. So the weight force is 100 times 9.8, which is 9,800 newtons, applied over an area of 20 square meters. So 980 divided by 2 is 490. So the pressure is 490 pascals. Now let's say if we have a very tall container that is filled with water, and let's say the container is sealed, so it's not open to the atmosphere. How can we calculate the pressure at this point in this container? So it's filled with water. How can we find the pressure? Let's say it's a very large tank, and we want to find the pressure 5 meters below the surface. What can we do? So we know that pressure is force divided by area. So the force is going to be the weight of the water, mg, that is currently above this surface where the point of interest is located. So the mass of water exerts a downward force on its cross-sectional area. And that weight force is the mass of the water above it times the gravitational acceleration divided by the area. Now, because we have a fluid, it's best to think of the mass of a fluid as being the density multiplied by the volume. Remember, density is mass over volume. So mass is density times volume. So let's replace M with PV. So the pressure at that surface is the density of the fluid times the volume of the fluid above it multiplied by gravitational acceleration times the area. Now the volume of the water above it is basically the volume of a rectangle. Which is the length times the width times the height. So the volume, as you mentioned before, is L times H times W. Now length times width will give us the area of this surface, which is basically the area of this surface here. So length times width is area, so volume equals area times height. So let's replace V with area times height. So the pressure is going to be the density times the area times the height times gravitational acceleration divided by the area. So we can cancel A. Therefore, the pressure due to the water above this cross-sectional area is equal to the density times the gravity times the height. So now we can calculate it. The density of water is about 1,000 kilograms per cubic meter times G, which is 9.8, times 5 meters. So it's basically 5,000 times 9.8. So the pressure due to the water above that point of interest is 49,000 pascals. Now, what would be the pressure if this container was not closed, if it was open to the environment? In that case, the pressure at this point would be higher because you have the weight of the atmosphere pushing down on the fluid. So in this case, the pressure at the point of interest is going to be called the absolute pressure, that's P, and that's equal to the pressure of the atmosphere plus the gauge pressure. The gauge pressure is simply the pressure that is above the atmosphere. The atmospheric pressure is 101,300 pascals, and the gauge pressure is the pressure due to the weight of the water above that cross-sectional area, so that's the 49,000 pascals. So the absolute pressure at that point is going to be 150,300 pascals. Let's try another problem. Let's say if we have a container that's open to the atmosphere, and we have water, and we also have, let's say, oil. The density of the water, we know it to be 1,000 kilograms per cubic meter, and let's say the density of the oil above it is 700 kilograms per cubic meter. And let's say that the height of the oil is about 4 meters, and the height of the water is about 5 meters. And let's not forget that we have the weight of the atmosphere, basically the weight of all the air molecules above this fluid pressing down on it, exerting its own pressure. So what is the pressure at the bottom of this container? So that pressure, the absolute pressure or the total pressure at that point is the sum of the pressures caused by the weight of the water above that point plus the weight of the oil and the weight of the atmosphere. So the pressure, or the gauge pressure due to water alone, is going to be the density of water times the gravitational acceleration times the height. And the pressure caused by the oil is the density of the oil times G times H plus the atmospheric pressure. The density of water is about 1,000, G is 9.8, and the height of the water is about 5, plus the density of the oil, which is 700 times G, times the height of the oil, which is 4, and then plus the pressure due to the atmosphere, which is 101,300 pascals. So 5,000 times 9.8, that's 49,000. That's the pressure due to H2O alone. And then 700 times 9.8 times 4, that's 27,440 plus the weight of the pressure due to the atmosphere. So if we add the three numbers, 27,440 plus 49,000 plus 101,300, the absolute pressure at this point, or the total pressure, is 177,740 pascals. So basically, you need to add the gauge pressure of the water and the gauge pressure of the oil plus the atmospheric pressure of the air, and that'll give you the total pressure at that point. Now here's a question for you. Let's say if we have a rectangular surface and it's 8 meters by 9 meters, and we want to calculate the total force exerted by the atmosphere on this surface. How would you do it? So we know that pressure is force divided by area. So the force exerted by the atmosphere on this surface is pressure times area. And the area of the surface is the length times the width. So the force exerted by the atmosphere is the pressure of the atmosphere, which is 101,300 pascals, times a length of 9 and a width of 8. So over this large area, the force exerted by the atmosphere is 7,293,600 newtons of force. So that's the entire weight of the air above this particular surface. So all of the molecules, imagine if this was one big vertical column that extended from the ground to outer space. The weight of all of the molecules in this vertical column is equal to this force right here. So that's the weight of the atmosphere above this surface, from the Earth to outer space. Now the next topic of interest is the hydraulic lift. Now this device is filled with a fluid. According to Pascal's principle, the pressure applied to a confined fluid increases the pressure throughout by the same amount. So the pressure that we exert on one side, let's call it the input pressure, is equal to the pressure exerted on the other side, the output pressure. So if we apply a force over this circular area, we're going to exert a pressure. And that input pressure is the input force divided by the area. And an output force will be exerted. And that output force divided by A2 is equal to the output pressure. Let's call it F2. So if we cross multiply, we're going to get the equation F1 A2 is equal to F2 A1. And if we solve for F2 by dividing both sides by A1, we get this equation. F2 equals F1 times the ratio of the areas A2 over A1. So let's make some more space. Now let's apply an input force of 100 newtons. And let's say that the area or the radius of that cylinder is 10 centimeters. And let's say the radius of this cylinder is 30 centimeters. What is the output force that's going to be exerted by this cylinder if we apply an input force of 100 newtons? So using this equation, F2 is equal to F1, which is 100 newtons, times A2, which is basically pi times the radius squared, over A1, which is pi r1 squared. Now we can cancel the pi values. So simply the ratio of the radius of those two circles. So R2 is 30 centimeters, but we need to square it. R1 is 10 centimeters, and we need to square it as well. So the unit centimeters will cancel. We don't really need to change it to meters. So it's 100 times 30 squared, which is 900, divided by 10 squared, which is 100. So F2 is equal to 900 newtons. Now let's think about what this means. The output force was increased by a factor of 9. It went from 100 to 900. So that means that the mechanical advantage of this machine is equal to 9, because it was able to multiply the force, the input force, by a factor of 9. Mechanical advantage is the ratio of the output force divided by the input force. Now, even though the force was multiplied by a factor of 9, it wasn't a freebie, so to speak. There was a cost for it. It wasn't free. So what was the cost that we had to pay to increase the force by a factor of 9? It turns out that the input work that you apply to this device is equal to the output work. So F1 times D1 is equal to F2 times D2. Now let's say if the hydraulic lift went up by 1 meter. That means that we have to apply a force of 100 newtons for a distance of 9 meters, because the work can't be increased. Now we can lose energy by means of friction, but let's say if we have a perfect ideal situation, the input work equals the output work. So the input work is basically a force of 100 newtons times the distance of 9 meters, which is 900 joules. The output work is the same. The machine applies a force of 900 newtons, but it only moves a distance of 1 meter. So it exerts 900 joules of energy. So there's no gain in energy in this system. So we basically apply a small force over a longer distance, and we get a larger force applied over a shorter distance. The concept is similar to that of a lever. A lever allows you to leverage your force to multiply it so you can lift a larger object. For example, let's say if the lever arm on the left side is 8 meters and on the right side it's 2 meters. If you apply an input force of 100 newtons, the output force is going to be 400 newtons. The torque created by F1 is equal to the force times the moment arm or the lever arm, which is perpendicular to the axis of rotation. It's actually perpendicular to the line of action, and it's between the axis of rotation or the pivot point. So that's the moment arm. So T1 is 100 times 8. So the torque on the left side is 800 newtons times meters. Now this creates another torque that has the same magnitude. 2 times 400 is also 800. But as you can see with the lever, the smaller force is associated with the longer side, and the larger force is associated with the shorter side. And the same is true for the hydraulic lift. The larger force is associated with the shorter side, and the smaller force is associated with the shorter distance. So now let's work on another problem with the hydraulic lift. So let's say if we want to lift a crate that has a mass of 800 kilograms, and we want to lift it by a distance of, let's say, 50 centimeters. And let's say that the radius of this portion of the hydraulic lift, let's say it's 60 centimeters, and the radius of this circle, let's say it's 10 centimeters. So what is the input force that we need to apply to lift the 800 kilogram crate by a distance of 50 centimeters? And also, what distance do we need to push down on the left side? And also, what is the pressure exerted on this surface? And what is the work that we need to apply to move this object 50 centimeters high? Calculate the work using two formulas. The first thing that we should do is find the output force. The minimum output force that we need to lift the 800 kilogram block or crate is the weight force. So F2 has to at least be equal to the weight force in order to lift this object up 50 centimeters. So F2 is equal to mg, which is 800 times 9.8. So the output force is about 7840 newtons. So now that we have F2, we can calculate F1. F1 divided by A1 is equal to F2 divided by A2. The input pressure is equal to the output pressure, according to Pascal's principle. So looking for F1, A1 is pi r squared, but like in the last example, we can cancel the pi constants. So it's just going to be divided by R1 squared, which is 10 centimeters squared. And we could leave it in units of centimeters. So A2, the pi is canceled, so it's just going to be R2, which is 60 centimeters squared. And F2 is 7840. So let's cross multiply. So F1 times 60 squared. Let's get rid of this. Is equal to 10 squared times 7840. 10 squared is 100 times 7840. That's 784,000 divided by 60 squared. And so F1, or the input force, is 217.8 newtons. Now, how can we calculate the input distance? How far do we need to push this particular cylinder down in order to lift the 800 kilogram block 50 centimeters up? What do we need to do to calculate the answer? The input work must be equal to the output work. And we could find the output work, which is the work required to lift an object against gravity. And whenever you lift an object above ground level, you're increasing the potential energy. So the work required is basically the change in potential energy, which is mg delta h. And the weight force, mg, is basically F2. And the change in height is basically the vertical displacement. So it's going to be force, which is 780 or 7840, times the vertical displacement in meters, which is 0.5 meters. 50 centimeters is half of a meter, and 100 centimeters is 1 meter. So half of 7840 is 3,920 joules. So that's how much energy is required to lift the 800 kilogram crate by 50 centimeters, which means that we need to apply the same amount of energy to push this cylinder down so that this cylinder can go up. So the input work and the output work are both 3,920 joules. So now that we know the value of the input work, we can calculate how far we need to push the cylinder down. It's going to be the input force times the input distance. So work is 3,920. The input force is 217.8. And let's solve for D. So it's 3920 divided by 217.8. So D is about 18 meters, which is pretty high. So we need to apply a force of 218 newtons, and we need to push this cylinder down by a distance of 18 meters in order to lift the 800 kilogram block by only half a meter. So there's no gain in energy. However, the force does increase. So what is the mechanical advantage of this hydraulic lift? The mechanical advantage is the ratio of the output force divided by the input force. So that's 7,840 divided by 217.8. So the mechanical advantage is about 36. So this particular hydraulic lift multiplies the force by a factor of 36. So if you apply a force of 100 newtons, the output force will be 100 times 36, or 3,600 newtons. Now it turns out that there's another way to calculate the mechanical advantage. The mechanical advantage of this hydraulic lift is also equal to the ratio of the input distance divided by the output distance. So we had to push the cylinder on the left by a distance of 18 meters, so that the 800 kilogram crate can go up by 0.5 meters. So 18 divided by 0.5 is 36. So there's a trade-off. If you want to increase the force, you have to apply a smaller force for a longer distance. So the work done is the same in both cases. Now the last thing we need to do is calculate the pressure exerted on the cylinder on the left side. So pressure is force divided by area. The force exerted on the left is 217.8 newtons. And the area is the area of a circle, which is pi r squared. 10 centimeters is 0.1 meters. So 217.8 divided by 0.1 squared. And let's take that result divided by pi. So this is equal to 6,933 newtons. Well, not newtons, but pascals, since this is now the pressure. So that is it for the hydraulic lift. So now the next topic of discussion is the Mercury Barometer. So let's say if we have a beaker, and if we have a tube, and it's filled with mercury. Now this barometer is open to the atmospheric pressure. So the weight of the air exerts a force. And the pressure inside is 0. So the difference in pressure is just the atmospheric pressure. With this information, how can you calculate the height of the mercury column? How high is it above this level? What's the difference in height? Now let's say that you know the density of mercury. The density of liquid mercury is about 13,600 kilograms per cubic meter. And you know the atmospheric pressure. So what is the height of the mercury column? Now to figure this out, we need to understand that the weight of the atmosphere, which is associated with the atmospheric pressure, balances out the weight of this mercury column. And the weight of the mercury column is associated with the gauge pressure. So we could say that because the weight of the atmosphere must balance the weight of that mercury column, the atmospheric pressure must equal the gauge pressure. And the gauge pressure is simply the density of the fluid times the gravitational acceleration times the height. Now we know the atmospheric pressure. It's 101,300 pascals. The density of mercury is 13,600. G is 9.8. So we need to solve for the height. So the height of the mercury column is about 0.76 meters, which is approximately 76 centimeters. Now let's say if we replace mercury with water. How high can the atmosphere support a column of water? How high will the water column be? So we can use the same equation, but this time the density of water is significantly less than that of mercury. So we should expect that we require a higher column to get the same mass of mercury. Mercury is 13.6 times more dense than water. So to get the same mass, we need a height that's 13.6 times greater than the height of Mercury. The density of water is 1,000. G is 9.8. Let's solve for H. So the height of the water column that the atmosphere can support is about 10.3 meters, which is very high. Now remember, the height of the mercury column was 0.76. So if you take 0.76 and multiply it by the ratio of the density of mercury by the density of water, you will get this answer. 0.76 times 13,600 divided by 1,000 is equal to 10.3. So that's another way you can get the same answer if you know the density of one material and you want to find the height of the other material. Let's try this problem. The height of mercury in an open barometer is 64 centimeters, and the height of another fluid is 154 centimeters. What is the density of the fluid, and what is the pressure of the air? So let's draw the open barometer. And it has mercury. So let's calculate the pressure of the air first. So the outside air is going to exert a pressure, and that pressure pushes up the fluid. So the weight of the air equals the weight of this column. So therefore, the pressure of the air is equal to the gauge pressure of that column, which is density times gravity times height. Now for this equation, the density of mercury has to be in the units kilograms per cubic meter. So if it's 13.6 grams per cubic centimeter, that's 13,600 kilograms per cubic meter. G is 9.8, and the height of the mercury column in meters. To convert centimeters to meters, divide by 100. So this is going to be 0.64. So 13,600 times 9.8 times 0.64. That's about 85,299 pascals. So that's the pressure of the air. Now what about the second part of the problem? What is the density of the other fluid? Now, the pressure of the air is equal to the gauge pressure of the other fluid, and that's also equal to the gauge pressure of mercury. So these two are equal to each other. So we could divide by the gravitational acceleration. Those two will cancel. So the density of the fluid times the height of the fluid is equal to the density of mercury times the height of mercury. So the density of the fluid, we're looking for that. The height of the fluid is 154 centimeters. The density of mercury, we can use the units grams per cubic centimeter. If we use those units, then the density of the fluid will also be in grams per cubic centimeter. And the height, we can leave it in centimeters because the height of the fluid is in centimeters. So the unit centimeters will cancel. So the density of the fluid is simply the density of mercury, which is 13.6, times the height of the mercury column divided by the height of the fluid column. So the density of the unknown fluid is 5.65 grams per cubic centimeter. So make sure you understand this. Because mercury has a higher density, the height of the column is going to be less than the height of the fluid that has a lower density. So water has a very low density, but the height of the water column is very, very high. It was about like 10 meters, which is 1,000 centimeters. But mercury, because it's very dense, it has a lot of mass per unit volume. the column for mercury is very low. And so that's why mercury is very useful to use for barometers, temperature gauges, is because there's a lot of mass per unit volume. Now let's say if we have a column, basically an open barometer with a column, and there's going to be two fluids. Here's the first fluid, and here is the second fluid. And let's say on the inside, the pressure is 0. So let's call this fluid A and fluid B. And the height of fluid B, let's say it's 30 centimeters. And the height of fluid A, let's say it's 25 centimeters. And let's say that the density of fluid A is 11 grams per cubic centimeter, and the density of fluid B, let's say it's 14 grams per cubic centimeter. So with this information, what is the atmospheric pressure? How can you calculate it if you have two different fluids? So the atmospheric pressure is the sum of the gauge pressure for fluid B, which represents or is associated with the weight of that column, plus the gauge pressure of fluid A. So it's going to be PA plus PB. So the gauge pressure for fluid A is the density of fluid A times the gravity times the height. And for fluid B is simply PGH as well. So the density for A, now we'll need it in kilograms per cubic meter, so that's going to be 11,000 times G, which is 9.8. And the height of fluid A in meters, 25 divided by 100, is 0.25 meters. And then plus the density of B, which is 14,000 times 9.8 times the height of B, which is 0.3 meters. And we just got to add the two gauge pressures. So 11,000 times 9.8 times 0.25. So the gauge pressure for fluid A is 26,950 pascals. Now for fluid B, it's 14,000 times 9.8 times 0.3. So it's about 41,160 pascals. So now let's add these two values. So the pressure of the atmosphere under these conditions is about 68,110 pascals. So that's how you can calculate it with an open barometer that contains two different fluids. Now let's say if we have an open tube manometer. But we're going to have two of them. So both manometers will contain mercury. But the shapes are going to be a little bit different. So on the outside, it's open to the atmosphere. So this is the atmospheric pressure. And we also have the atmospheric pressure on this side as well. And this is going to be the pressure of the gas, which we can just call it P. And then we have the height of the mercury column, or the height difference, which we'll call h. So how can you write an equation between the pressure of the atmosphere and the pressure inside the gas for each of these situations? So these two pressures, the pressure of the gas and the pressure of the atmosphere, they're going to differ by the gauge pressure, which is pGh. That's the gauge pressure of the mercury column. So how can we find out which equation will be which? So here's a question for you. Which pressure is stronger on the left side? Is it the atmospheric pressure or the pressure of the gas? Notice that the gas pushes down more on the mercury than the atmospheric pressure for the picture on the left. Therefore, this pressure is greater than the atmospheric pressure. And it differs by the gauge pressure of the mercury column. So P is equal to the atmospheric pressure plus the gauge pressure, which is the density times gravity times the height of the mercury column. Now on the other side, the air pushes down more on the mercury column than the gas. So the atmospheric pressure is stronger. So therefore, the atmospheric pressure is equal to the pressure of the gas plus the gauge pressure. So let's work on some examples. Now let's say if we have a fluid, let's say it's some type of oil, and the height difference is about, let's say, 40 centimeters. And the density of this oil, let's say it's pretty heavy. Let's say it's 3 grams per cubic centimeter. And let's say the pressure of the gas is 30 kilopascals. Or rather, let's say the pressure of the atmosphere is simply 101.3 kilopascals. What is the pressure of the gas? So first, we need to find out which pressure is greater, the atmospheric pressure or the pressure of the gas. So the atmospheric pressure pushes down more on the oil than the gas. So the atmospheric pressure is greater than the gas. So the atmospheric pressure is equal to the pressure of the gas plus the gauge pressure of the oil. So that's going to be P plus pGh. So we already have the atmospheric pressure, which we know it to be 101,300 pascals. And this is equal to the pressure of the gas plus the gauge pressure of the oil, which is the density of the oil in kilograms per cubic meter, which is 3,000, times G, and times the height of the column, which is 0.4 meters. So 3,000 times 9.8 times 0.4 is about 11,760. So the pressure of the gas is 101,300 minus 11,760. So it's going to be 89,540 pascals. So that's how you can calculate the pressure of the gas inside a manometer. You simply need to add or subtract the gauge pressure either from or to the atmospheric pressure. And just ask yourself, is the gas pressure, is it less or greater than the atmospheric pressure? and then you can either add or subtract pGh to it. So the pressure that's greater is the one that pushes the fluid further into the manometer. Because the fluid is at a higher level on the right side, that means the pressure of the gas is less than the pressure of the atmosphere. Here it's lower, which means that this pressure is greater. It exerts a greater downward force.